timetables about the room change for tomorrow. Okay, so coming back to the matter at hand, we're going to start this chapter 6. So chapter 6 partners with chapter 7. These are polynomial congruences 1 and 2. And here's where we're going to be studying the solution of polynomial congruences. Okay. Now, what's a polynomial congruence? Well, similar, you're familiar with the idea of solving a polynomial equation, finding the roots of a polynomial function. Well, here we're going to be doing something quite similar. In one sense, is finding the solutions of not an equation, but of a congruence. Okay? So we're going to be trying to solve this kind of setup, where you've got a polynomial function f evaluated at an argument x, where we're looking for solutions of it being congruent to 0 modulo some modulus m. Okay. So in one sense, we're kind of quite familiar with this kind of a setup because we're familiar with the idea of solving polynomial equations. For polynomial equations of low degree, quadratics and so on, we've got the quadratic formula for solving it, and there are similar formulas for cubics and quartics. But once you get to higher degrees, there are no longer exist kind of simple, straightforward formulas for getting solutions, but we do have numerical results for approximating solutions of polynomials of higher degree, of course, as well. Okay. So just to be clear in the setup, we're going to be dealing with polynomial functions with integer coefficients. Because we're dealing with congruences and moduluses, we want to stay within the realm of integers for all of this, okay? So our functions f will be polynomial functions, but with integer coefficients. So there won't be any fractional quantities coming into it. Okay? So just to say a little bit, okay, so we've been referring to polynomial equations. In polynomial equations, we have an important theoretical result, or an important classifying result called the fundamental theorem of algebra, and that says that any polynomial function, any polynomial with real coefficients or indeed complex coefficients, if the polynomial function has degree n, then the polynomial will always have n complex roots. But they may need to be counted with multiplicities. Sometimes you can have a root of a polynomial occurring with a higher multiplicity, of course, okay? But there's this really nice result, really nice clean result that a polynomial of degree n has n solutions in the domain of complex numbers. So our first task will be to have a quick look at some examples because, you know, we might hope that, well, if the fundamental theorem of algebra is true for solving polynomial equations, maybe there's a very similar result for polynomial congruences. Okay. So our first task is going to discover, by means of looking at a few examples, that really the story for polynomial congruences is not so straightforward, or there's no such clean overall underlying result as that fundamental theorem of algebra for polynomial equations. Okay. Okay. So we'll do some initial investigations into this. I'll deal with a couple of these examples that are discussed there in the notes, but I'll just deal with them on the overhead as well, just so we can discuss them a bit more. So first of all, we'll just be clear on what we mean by solutions. So what do we mean by the solutions of a polynomial congruence? Okay. So we want to refer back to chapter 4. So recall from chapter 4, where we first introduced the notion of congruences and modular arithmetic. We proved this nice result here, that if we had two arguments, we had two numbers, x and y, which were congruent modulo n. We have two integers which are in the same congruence class, modulo something. that implied that if you evaluated a polynomial function f at both of those arguments, while you probably got different integer answers, so x and y are probably different integers, in the same congruence class modulo n, but they're probably different integers. So when you evaluate the polynomial f at x and y, you'll probably get different values. But what we proved was, despite the values being different, they will always belong to the same congruence class modulo n. And this is true for any polynomial f with integer coefficients. So what that means is, when we talk of what the solutions to a polynomial congruence are, what we're going to mean are we're going to be finding certain congruence classes as the solutions. So the solutions to a polynomial congruence f of x congruent to 0 mod n, if they exist, they'll be congruence classes of integers. So on the one hand, the solutions will be individual integers. So we might find that x equals 1 is a solution of this, or x equals 4 is a solution of this. Okay? But really, what we're discovering will be whole congruence classes modulo n as being solutions. Okay? So if we do find that, say, x equals 1 is a solution of this, but this result from chapter 4 tells us, well, if we take any other number that's congruent to 1 modulo n, that will also be a solution of it. Okay? And we don't want to count that second solution, as being a genuine second solution. So if we take anything congruent to 1, if x equals 1 is a solution, if we take anything else congruent to 1 modulo n, that will also be a solution. We're not discovering new solutions all the time there by looking at different integers congruent to 1 modulo n. We're just encountering the same solution again and again and again. Okay? So the objects that solve these things are whole congruence classes of integers modulo n. Okay. So then the question becomes slightly different. We know that there are m congruence classes of integers modulo n, everything congruent to 0, 1, 2, 3, all the way up to n minus 1. Those are your m congruence classes modulo n. Then the question will be, which of those solve the polynomial? Okay, so let's look at a couple of examples. Some simple examples. The polynomials won't be too complicated. So 2x congruent to 3 modulo 4. Okay. It's not too hard to discover all the solutions of this, because there's only 4 objects to test. Okay, there's only 4 congruence classes modulo 4. So we've only got 4 things to test. So we can, without being sophisticated at all, we can simply try each possibility. Okay? So checking, 2 times 0 is obviously congruent to 0. 2 times 1 is obviously congruent to 2. 2 times 2 is congruent to, is equal to 4, but that's congruent to 0 mod 4. And the last congruence class 3, 2 times 3 is 6. The standard representative for that is 2 modulo 4. So quickly checking all possibilities, we find that we never get 3, so there's no solutions. I certainly don't need to go checking any other possibilities for x. I don't need to check x equals 10 or x equals 17, because whatever other integers I try for x, they will always be congruent to one of these, modulo 4, okay? Because this is a complete set of residues, modulo 4, 0 through 3. So by just, really unsophisticated, just brute force checking all the possibilities, we find we never get 3, so there are no solutions. So this polycongruence, okay, it's just a simple polynomial 2x minus 3. we're trying to solve that congruent to 0 modulo 4, this polycongruence has no solution. Now you might have already spotted that straight away, because you can reason like this. Well, we're trying to get the congruence class of 3 modulo 4. All the integers that are congruent to 3 modulo 4, they're all odd integers, okay? Because it's 3, and anything which is a distance, a multiple of 4 away from 3. But 4 is an even number, so anything that's a multiple of 4 away will be an even distance away from 3, so that they'll all be odd integers. Okay? 3, 7, 11, all those things congruent to 3 mod 4, they're all odd integers. But of course, here on the left-hand side, we've got an even integer, 2 times x. So 2 times x can never be equal to anything that is congruent to 3 mod 4. So by checking the odd and evenness, we could have seen more mathematically, more sophisticated argument, we could have seen that there's no possibility for a solution as well. Okay? So sometimes polynomial congruences can have no solutions at all. So already that's quite different from the situation for polynomial equations. Because polynomial equations, at least in the domain of the complex numbers, always have a full set of solutions that add up when you add their multiplicities up, come to the same as the degree of the polynomial. We'll look at a second example, which is x squared minus 1 being congruent to 0 modulo 8. Okay, so 8, there's still only 8 possibilities, so we can check them all. 0 squared minus 1, well, that's minus 1, but we maybe think of that as 7 modulo 8. 1 squared minus 1 is quite clearly 0. Okay, so we do have a solution. 1 is a solution. 2 squared minus 1, so it's 3. 3 squared minus 1, so it's 9 minus 1 is 8. Okay, so that's 0. 4 squared is 16, minus 1 is 15, but that's the same as 7 mod 8. Let's do some other ones. 5 squared minus 1, 5 squared is 25. Subtract 1. Get 24, and that's 0 mod 8. 6 squared is 36, minus 1 is 35, and 35 is 3 mod 8. And lastly, 7 squared is 49, minus 1, 48. That's congruent to 0 mod 8. Okay. So all of these are mod 8. So quickly checking all 8 possibilities, you see we do have some solutions. Got 4 solutions. But these are different solutions because they're different congruence classes modulo 8. The congruence class of 1, congruence class of 3, congruence class of 5, and the congruence class of 7. So we've got 4 separate, distinct congruence classes mod 8 that provide solutions of the polynomial congruence x squared minus 1 is congruent to 0. Remember, just as before, I don't need to check any other integers. I don't need to check any other positive or negative integers, because whatever other integer you care to mention, it will be congruent to one of these 8, 0 through 7. Okay? So that's a complete set of representatives of all the congruence classes in modulo 8.
Do you write the answer? Is it x is congruent to 1 is congruent to 3?
Yeah. So we have 4 solutions. 4 solutions, that is, x is congruent to, what did you say? Yeah, 1, 3, 5, and 4, 7. Yeah. Yeah, so you quote your four solutions like that. Now, if you're talking about individual integers, of course, there's an infinite amount of integers that solve this. Okay, because anything congruent to any of these any integer congruent to any of those will be an integer solution to this, so there's an infinite number. But we've already agreed, because that's true anyway, the things we're going to count as solutions is not individual integers, but congruence classes of integers. Okay, so we've got four of the 8 congruence classes are a solution. So what we're seeing in these 2 examples kind of destroys any hope that the situation in polynomial congruences is the same as that for polynomial equations. Polynomial equations, we always know there's n complex solutions counted with multiplicities, where n is the degree of the polynomial. But already, even just with linear order 1 polynomials and order 2 polynomials, we're seeing a range of behavior. A polynomial with no solutions at all, and a polynomial with 4 solutions, but it's only got degree 2. So it's got loads of solutions compared to the degree of the thing. So the situation seems harder to describe compared to polynomial equations. Okay, the discussion in that first section in the notes is really just going through those points. So we got quite a task now, is to build up the theory of polynomial congruences. Okay, so it is possible to describe, and come up with methods of solution for these. Okay, so that's what we're going to start to look at. Any questions so far, just about those examples? Okay. Okay, so this first chapter deals, so we want to approach this systematically. So one way of approaching it systematically is to deal with a simple case first. So a simple case, if we're talking about polynomial problems, maybe one of the early simple cases will be where the polynomial only has degree 1. Okay, so there's no x squared, it's x cubed, etc. It's just degree 1. So it's something times x plus a constant term, and we're looking for zeros of that. Okay? So simplest cases will be linear polynomials. So now the results are in the notes there, but we'll just do a bit of an introduction or a kind of a discovery of some of the possibilities just with a few examples before we look at the kind of formal general results. Okay, so we'll be trying to solve this kind of ax congruent to b modulo n. Okay. That's the general form of a linear polynomial. So the polynomial is ax minus b, and we're looking for roots. Ax minus b congruent to 0, or presented like this, ax congruent to b modulo n. Now, okay, we've been studying congruences quite a lot, so we already know quite a lot of things. I mean, if you're faced with a problem a times x equals b, or a times x is b, I mean, what's your immediate intuition about trying to solve that? Well, if this was an equation between numbers, we'd immediately solve that by saying x is equal to b over a. Yeah, just divide both sides by a. Now, does that apply in this situation? Well, we're dealing with modular arithmetic, so we don't talk about dividing both sides, but we would talk about multiplying both sides by the inverse of a. And of course, then we have to remember, not everything has an inverse modulo n. Okay, but there might be an inverse to a modulo n. So if a inverse modulo m exists, this thing can be true if and only if this is equivalent to x being congruent to a inverse times b modulo n. So there's only one solution. One solution modulo n. There's only one congruence class modulo m which solves this problem, and it's the congruence class of a inverse times b, whatever that is. Okay? If we knew what the a and the b were, we could work out what the a inverse times b is. Okay? But of course, this only applies if if A inverse mod m exists. And remember, A inverse mod m exists we know exactly when these exist and when they don't. It's a nice condition on A and M. So an integer has an inverse modulo m only if the integer is co-prime to m. So in other words, that A and M, that their greatest common divisor is 1. Okay. So, I mean, let's check a quick example of this. So certainly in some situations, it's very easy to deal with linear congruences. If the A is co-prime to M, there's only one solution, and it's given by A inverse times. So e.g., let's think about 4x congruent to 7 mod 15. Well, the GCD of 4 and 15 is 1. 4 is co-prime to 15. So 4 inverse exists. I won't keep writing mod m all the time. This is mod 15 we're talking about. What is 4 inverse? So you're looking for something, when you multiply it by 4, you get something congruent to 1 modulo 15. Good. 4 times 4 is 16, which is congruent to 1 modulo 15. So it is self-inverse. It's its own inverse. Okay. So if we multiply both sides by 4, we're allowed to do, and it's an invertible step. You can undo that operation as well because you've got the inverse of 4. Just multiply it again by 4. And so if you multiply both sides by 4, so this original polynomial is equivalent to x being congruent to 4 times 7, which is 28, or which we normally write modulo 15 as 13. Yeah. So that's our solution. There's only one solution, and it's 13. Or the congruence class of 13 modulo 15. So any integer which is congruent to 13 mod 15 will be a solution of that. Okay? And there aren't any other ones. Okay? Because this is a logical equivalence. 4x is equal to 7, that implies x is equal to 4 times 7. You multiply both sides by 4. And that's an invertible step. If x is equal to this, multiply both sides by 4, you get 4x on the left, and the 4 times 4 is 1. You get back to 7. Okay? So there's only one solution. So we now completely understand this. We can say that we completely understand AX congruent to B mod M if A and M are co-prime. Don't we? If A and M are co-prime, the inverse to A exists, multiply both sides by A inverse, X has to be congruent to A inverse times. End of story. So then the question is, okay, well, what if it isn't co-prime? What if it isn't co-prime? Can there still be solutions? And how many of them might there be? So what if GCD of A and M is not equal to? Okay, let's have a look at some examples like this. So let's try 6x congruent to 7. Now we're maybe want to try and avoid brute force checking all the possibilities because there's 15 different congruence classes to check. Okay, so I don't want to do multiply 6 by 7 15 times and see if it's congruent to 7. I mean, I could do it, get the computer to do it easily enough, but we'd like to try and understand it a bit more mathematically. So now we're not able to say multiply both sides by 6 inverse because 6 inverse does not exist. Okay, there is no inverse to 6 modulo 15 because 6 and 15 are not co-prime. GCD of 6 and 15 is 3. So there is no element 6 inverse to multiply by 7 to give you a solution. Okay, so that's not available to us. So if there is a solution, let's start examining it and see what we can arrive at. If there was a solution, we'd be able to say 6x was congruent to 7 modulo 15. The meaning of that is that 15 divides the difference. Yeah? That's the meaning of being congruent to each other, modulo 15. So the meaning of dividing means that 6x minus 7 is equal to 15 times q, or some q. And that equation could be rearranged to say that 7 is equal to 6x minus 15q. Can anybody see a problem there? Can't even see it. That's a problem. When you can see it, is there still a problem? So what we're doing is we're investigating here, what's the consequence of a solution existing to this? So unraveling the definitions, the definition of modulus 15 divides this. Definition of divides means there exists a associated factor, multiply by the 15 to give you that. So x and q are integers, supposedly. Is this sitting well with you, or is it making you feel queasy? Yeah, good. No. So you're feeling queasy? You should be looking at that. You should all be feeling nauseous looking at that. Why should we? What's wrong with it? Sorry? Yeah, okay, there's two unknowns. So, but I'm posing the question, could there be an x and a q that solve that? No? What? Why not?
You can't do each values what?
Sorry?
You can't do each values what works there.
Why? Can you explain it simply, or? Why are you so sure that you can't?
Because 6x has to be smaller than 15.
No. X and q can be positive or negative integers. It's good you feel that this looks wrong, but can anybody pin the nail, hit the nail on the head? Why is it?
Will the right-hand side always be a multiple of 3?
Yeah, look. 6 is divisible by, so remember 3 was the greatest common divisor, so that's playing a role here. The right-hand side is definitely a multiple of 3. Because this is equal to 3 times 2x minus 5q. X and q are integers, supposedly. So look, the right-hand side has a factor of 3. Does 7 have a factor of 3 in it? Nope. It doesn't. So can this equation ever be true? Nope. So there can never, now, but there was nothing wrong with the logic from 6x being congruent to 7 to get us to here. There's nothing wrong with each of the individual steps. I was just unraveling the definitions. So there must be something wrong with this. So if 7 is not a multiple of 3, but this is false, that means the original one must be false. It can never be true. There is no x to solve. So this last equation, this last statement is clearly false. Three is not a factor of 7. So there are no solutions. There are no possible x's that will make this work. No solutions. To 6x being congruent to 7. 15. Okay, so what, I mean, okay, so that's a specific example, but let's try and pick out some general behavior there. Could we replay this argument? No. In what general situation could we replay this argument? Well, this 3 that occurs here is the same 3 as up here. It's the greatest common divisor of the 6 and the 15. Okay, so this 3 here is exactly the same thing. 3 up above. So those are the same number, not just a coincidence. And the fact that this number did not divide 7 means no solutions exist. So we can see a general result here. If the greatest common divisor of 6 and the modulus does not divide, whatever it is, the greatest common divisor, if that greatest common divisor does not divide the constant term, then no solutions are possible. Okay, so you can see a general result there. That's good. This is a situation whereby looking at individual examples and picking out what's going on at them, we can discover the general results. So we already understand it when the inverse does exist. Now we understand it when the inverse doesn't exist, but the greatest common divisor between A and M does not divide the constant term. So the only case remaining is when it does divide the constant term. So let's look at another example where we replace the 7 with something which can be a multiple of 3. So what if the constant term is divisible by 3? By 3, I mean the GCD of A and M. So let's look at an example of this. So let's look at 6x. I'll keep the 6 and the 15. But just instead of a 7 there, consider a 9. So, okay, using the same argument, that will reduce to 9 being 3 times 2x minus 5q, as before. Okay, so 6x congruent to 9 is the same as saying that 9 is equal to 6x minus 15 times some integer q. It's just the same sequence of steps we made before. Now here, this doesn't look strange, because 3 is a factor of 9. So we can simplify it a bit by dividing by the 3. So 3 is equal to now 2x minus 5q. But what's that really? That situation is equivalent to 2x being congruent to so do I want to say 3 or minus 3? 6x.
You want to
I'm going to
say
say 3. Yeah. But not modulo 15, modulo 5.
Wait, what is a cube?
So our original congruence now seems to be equivalent to this slightly simpler one. Simpler because the modulus has decreased in size. Okay. But is this covered by any of the previous cases we've looked at? Well, yeah, because the 2 is now co-prime to 5. So an inverse of 2 exists. So that's true if and only if x is equal to 2 inverse times 3, or 5, and 2 inverse does indeed exist. Inverse modulo 5 now. 2 inverse is 3 mod 5. So we seem to have x being congruent to 9. Sorry, 9, but rather than 9, I should say 4. 4. I mean, 9 is not incorrect, but we normally try and quote these things using the standard reduced representative. So there are solutions here. the original problem is equivalent to x being congruent to 4 modulo 5. So anything congruent to 4 mod 5 is a solution to that original problem. But now, the original problem was posed modulo 15, but now we're quoting a solution modulo 5. But maybe we'd like to quote the solution not modulo 5, but quote it modulo 15. In the terms that the problem was originally posed. And what we discover here is, see, what are some other things congruent to 4 mod 5? Well, you've got 9, 14, and 19. You have another 5. These are all things in the same congruence class modulo 5. But what we see here are 3 different congruence classes modulo 15. So that's actually equivalent to saying x is congruent to either 4, 9, or 14 modulo 15. Okay? Any integer which is congruent to 4 mod 5 can be put into one of these 3 congruence classes modulo 15. Okay, so 4, 9, and 14, they're all congruent to 4 mod 5. They're all in the same congruence class modulo 5, but they represent different congruence classes modulo 15. So what we found here is we found 3 different solutions. I won't list 19 again as a fourth solution. Why not? It's the same as this solution there. Yeah, 19 is congruent to 4. And I won't list the next one after 19, 24, because that's congruent to 9. So these are all of the solutions modulo 15. So there are 3 solutions to the original problem. And again, this 3 is not a coincidence. The fact that this is 3, let's put a box around it, is the same as this 3 up here, which was the GCD of A and N. That's maybe not so immediately obvious, but you know, when you track it through, this 3 here is a coincidence that it's the same as that 3, because that's the other factor. It was in the 9 after we cancelled the 3. So there's a lot of 3s there, but the fact that that's 3 there, the GCD of 6 and 15, that's the same 3 that's counting the number of distinct solutions there. So now we see we can start to pick out another general result. Okay, this is all specific for one specific problem, but the steps that are taken there, messing around with the GCD, dividing both sides, etc., you can start to pick out the general result. If you have a polynomial congruence, where the 6 is not coprime to 15, so it has a non-trivial GCD. If it does divide the constant term, there will be solutions. We can track them through like this, and the number of distinct solutions we have will be the same as, will be the same as the original GCD. So that's the last general results that we're going to discover here for linear congruences. Sorry, do you have a question? So 4, 9, 14, what I was doing here was investigating some of the other integers that are in this congruence class of 4 modulo 5. I was looking at some of the other representatives of that congruence class. So I'm just adding multiples of 5 onto 4. 4 goes to 9. So all of these numbers, you could continue this list, all of these numbers are congruent to 4 mod 15. So these aren't distinct, they aren't distinct congruence classes modulo 5, but they are distinct congruence classes modulo 15. There's 3 of them represented here. Yeah. So you just, when you're changing moduluses, you know, using different moduluses and different statements, you just have to be a little bit careful and always be clear what moduluses you're talking about at any one moment. Okay. Okay, that's used up all our time this morning. Tomorrow afternoon, we'll look at the general proofs of these results. There's nothing essentially new from what we've seen at work in these examples, but we'll just set it all on a good general footing. And by the end of tomorrow, then, we'll have a complete understanding of linear congruences. Okay?